Okay, today we're going to jump in and we're going to work our way through solving trig equations. So you see the title at the top of the screen, and there's going to be our instruction that we're going to go through and we're going to follow for the entire day. So if x is greater than or equal to 0 and less than or equal to 360 degrees, find the possible value or values of x. And I just want you to take a look at that first equation, cos x equaling 1/2. And I want us to recognize why we have a trig equation. Notice where your variable is. It's inside your trig ratio. So just the same as an exponential equation was called exponential because the variable was in the exponent, a trigonometric equation is one where the variable is inside our trig ratio. So now that we can see the sort of equation we're going to have to solve, I want to go back to the instruction for a moment. First off, you see the restriction that's been labeled on x. I just want us to put an idea in our head, and this is a revisit from what we dealt with in last lesson, that anytime we see x is greater than or equal to 0 and less than 360 degrees, let's make sure that we're viewing that as one positive rotation. That's all that means. So if I was to reread the instructions for today, I would say, well, if x can make one positive rotation, then find the possible values. So let's take a look at the first one. We're going to actually jump in and we're going to solve. So cos x equals 1/2. Now, for us to go through, this has actually been an equation that you've solved a number of times. It just would have looked like something like this. You would have had a triangle, and on that triangle, we would have had an angle, for instance. You would have been given two sides, and you would have been asked to solve for the value of x. Find the angle. Notice this is the exact same thing as what we have in our equation, because the number that we have on top would be my adjacent side, since we talk about cos, and the number that I have in bottom would be my hypotenuse, since we're talking about cos, and cos is adjacent over hypotenuse. So from angle x, you would now have an adjacent side and hypotenuse, and you'd be asked to find the angle. This in grade 10 would be a calculator problem for us. It is no longer a calculator problem. So I want us to be able to work our way through and be able to solve this with no calculator. And for most of us, because we've got some practice in and we've been good at dealing with our special triangles, we should be able to come up with what that angle measurement is for x. What I want to do is I just want to show you a way that you can structure your solution. So first off, let's put down a quick set of axes. And this is going to be the first step for us to solve all trig equations. Now what I can do is I can construct my triangle. So all I'm going to do is I'm going to create my triangle, rotating an angle measurement of x, where my adjacent side would be 1 and my hypotenuse is 2. And now, when we take a look at that triangle, we should be able to recognize, though it would never be required to label, that I actually have a special angle. I have my 1√3(2) special triangle. And since my opposite side is the big side, that means that my x has to be the big angle. And we could then state that therefore x would have to equal 60 degrees. So for us to be able to work through should be pretty straightforward. Now, I want to come back up to something in the problem, and you may have noticed the plural potential on values. For us to be able to work through, I'm hoping that we maybe recognize that there would be another solution to this equation. And this is where I want to kind of come back to, would there be another triangle that you could draw that would have an adjacent side of 1 and a hypotenuse of 2? And perhaps we could think of, maybe my triangle could have existed down here. I would still have an adjacent side of 1, and I could have that hypotenuse of 2. It would mean that my opposite side would be negative root 3, but that still doesn't change the value of cos. It would still be positive 1/2. And so what would that angle measurement be if I had to rotate all the way around to my fourth quadrant? Well, because of the special angle, we should be able to recognize that I would still have the same related acute angle, 60 degrees. And so if I was to rotate all the way around into the fourth quadrant with a related acute angle of 60 degrees, that I could have come up with another angle measurement of 300. Now, take out your calculator and punch in some quick confirmation, but we should also be able to do that without a calculator and confirm that the cos of 300 is also equal to 1/2. So, big notion for us as we move forward. When we're solving trig equations, and I'm just jotting this down super fast, then there could be two solutions. And so, what do we always do as we go through to solve trig equations? We examine the rotation angle. So, what we're going to do is we're going to spend our day today working through some rotation angles to be able to solve trig equations. Now, one of the items that I want to kind of address is some ways for us to examine where the two possible solutions of a trig equation could exist. That we wouldn't actually work through it the way that we did problem A, that we could be much more efficient in getting there. What I'd like you to do is just examine the 4 quadrants that I've listed on the picture. You'll notice that in each one of those quadrants, I've used my rotation angles to go around and determine the sine of each trig ratio. And so you'll see those listed in each quadrant. Okay, the first thing I'd like you to notice is that there is no 2 quadrants that have the same sign for all 3 trig ratios. So for instance, you'll notice in the first quadrant, all 3 of our ratios are positive. You'll notice that never occurs again. You'll notice that in all the other quadrants, 2 of your ratios are negative, 1 of them is positive. And that combination never occurs again. And so as you start to rotate around, there happens to be an acronym that some people use to be able to determine which one of those quadrants your trig ratio is positive. And so if you notice in quadrant 2, my sine ratio is positive. In quadrant 3, my tan was positive. In quadrant 4, my cos was positive. And in quadrant 1, all of them were positive. Because of the nature of all of those signs, some people use what's called the cast rule. And maybe you can see cast spelled out as an acronym in each one of those quadrants. This is just being mentioned so that if you hear anybody say, hey, I've got this quick way to be able to go through and deal with cast rule, then this is a means to be able to solve a trig equation. We are not going to be using cast rule to solve trig equations. It is something you can fall back on. However, as we start to grow and we start to expand our experience in trig with trig functions, you're going to want to have a better way to be able to determine those equations. Cast rule has some snags, and we're going to address a couple of those today. If we're not going to use cast rule then to be able to go through and deal with our trig equations, then I've got to give you a better way to deal with it. And this is the best way that I've come across to be able to solve. What we're going to do is we're going to use nothing more than grade 10 SOHCAHTOA and grade 7 integers. So what we're going to do is we're going to use all the stuff we already have in our background, and we're not going to have to need anything that is new. So let's examine it in its bits. The first thing that I want to deal with is let's address our sine ratio. You know how to calculate sine. Sine is always opposite over hypotenuse. However, because when we calculate the sine of any of these trig ratios, your hypotenuse is always positive. It's always positive. Then we don't care about it. That really, as we work our way around, all I ever need to remember is that sine is the opposite side. And so when we go through and we produce a triangle out of our rotation angle, the opposite side is always your vertical side. Okay, I forgot that we need a little bit of grade 9 of plotting points. Because when we talk about the opposite side, that opposite side being vertical, then we know that if we have a positive value, that means we go up. And if we have a negative value, that means we go down. And it's that simple. Okay, let's keep building it so that we can see it in practice. The next thing we can deal with is our cos ratio. We know that cos is adjacent divided by hypotenuse. But because hypotenuse is always positive, who cares about it? How do we find the adjacent side on our triangles? Well, every time we rotate and construct a triangle, our adjacent side becomes the horizontal side. And if we have a positive horizontal side, then that means we go to the right. If you have a positive x coordinate, you move to the right. And if we have a negative horizontal side, then we move to the left. It's that straightforward. Okay, I want to now come to the one that's maybe going to be a little bit extra to deal with, and that is our tan ratio. Now, why may the tan ratio be a little more? Because how do we calculate tan? Tan is opposite over adjacent. And notice that since tan doesn't use the hypotenuse, therefore the top and the bottom of that fraction could change signs. My opposite side could be positive or negative. My adjacent side could be positive or negative. So this is the ratio where I have to consider both. Well, that means then that I'm going to have to go and I'm going to have to deal with some grade 7 integers. The conclusion I can make is if I was to have a fraction that was positive, then the way a fraction can be positive is my top and my bottom must be same signs. If my fraction was negative, then the only way I can make a fraction negative is if the top and the bottom are different signs or opposite signs. Now, I just want you to take a look at my 4 quadrants again and notice that those 3 kind of background skills, concepts that we can tie together can put me in any one of those quadrants. And so when we go through to solve trig equations, what I really want us to think about, big star, is to think coordinates. If we do that, then you've got everything you need in your background. So let's jump in and start solving some trig equations. Okay, so let's take a look at that first one in question B. Sine x equals negative root 3 over 2. What I want to do is I want to walk through this one the way that I would solve a trig equation. So the first thing I focus in on is what is my ratio? And it's my sine ratio. Sine means opposite. So I'm talking about my opposite side. Now I tie with that the sine. I notice that my ratio is negative. And if my opposite side is negative, that tells me that my rotation, my terminal arm, must put me down. And so right away, I know that my terminal arm must be in quadrant 3 or quadrant 4. Okay, well now all I have to do is finish off building. So the next thing I can do is build my triangle, which means I drop in a height. And given that this is the sine, and I know that sine is opposite over hypotenuse, then I can label my sides. So my opposite side must be negative root 3. My hypotenuse must be 2. Now, you can choose to label the third side in the triangle, but it's never required. You've been asked to solve for the angle. So the most important thing I can come up with now is my related acute angle. And if we recognize those sides, then perhaps we can see that this would have been a negative 1 and 1. But more importantly, we recognize that that would be the sides of a 60-degree special triangle. And if I know my related acute angles, then therefore I can solve for x. I know that to get into quadrant 3, I would have to rotate 180 degrees plus 60 degrees. So 240. Or to get into quadrant 4, I would have to rotate all the way around, but be short 60 degrees. Therefore, 300 degrees. And there is a solution to that trig equation. There's our process. And that's the way that we can work our way through to be able to solve. Now, you might see one of the shortcomings of CAST rule. CAST rule uses the acronym that tells you which quadrant each one of those ratios is positive. Well, in question B, I gave you a negative. So for you to use CAST rule to solve for the negative, you have to think about the opposite case. I would argue to you, go directly to what you're looking for. So let's take a look now at the equation given in C. Tan x equaling 1. So first thing we do to be able to solve that trig equation is let's examine a rotation angle. Now I take a look and I'm dealing with my tan ratio. And I'm looking for tan being positive. And so when I examine my tan, I use my SOHCAHTOA. Tan is opposite over adjacent. Opposite and adjacent can both change signs. So therefore, I need to go to the quadrant where I have the same signs. That's going to put me into quadrant 1, where they're both positive, and quadrant 3, where they're both negative. So right and up, or left and down. Well, now that I have that, I can drop in my height, and I can label my sides. Tan equaling 1 tells me that my opposite and my adjacent are the same length. So opposite and adjacent are both 1s, or opposite and adjacent are both negative 1s. With those sides listed, I'm pretty good then to be able to say that I know that that would be the side lengths of my 45-degree special triangle. And now that I know the related acute angle, I can figure out what my principal angle is and therefore solve for x. So it's nice and easy. In quadrant 1, my rotation angle would be 45 degrees. And into quadrant 3, I would have to go 180 plus the additional 45, so there's 225 degrees. There we go. There's us working our way through being able to use special triangles to solve trig equations. And so now I want you to take a look at the equation in D, cos x equaling negative 1. And this one generally could cause some issues for some people. So I want to walk through this one kind of with the blinders on. I'm going to blindly follow the structure that we've been talking about today. So the first thing I do to solve any trig equation is examine my rotation angle. Now it tells me cos. Cos being negative, well, cos is adjacent, so if my adjacent side is negative, therefore I have to go to the left. And so my terminal arms could exist there. Okay, now I need to drop in my height. And now I need to label the sides. Well, if I go to label my sides of cos x equaling 1, I know that cos is adjacent over hypotenuse. And so if I have adjacent, well, I could view that as over 1. That means that my adjacent side is the same length as my hypotenuse. And maybe you can see then that if my adjacent side is the length of my hypotenuse, then there is nothing left for my opposite side. And so my opposite side then would have to be 0. And if my opposite side was actually 0, then my terminal arm should have been directly on the negative x-axis. And so when I solve that equation, then the only way I can get there is to rotate x being 180 degrees. So notice this one feels a little bit different to us because we didn't have two solutions, we only had one. And the reason why we only had that one was because our terminal arm was lying on an axis. So a couple quick things for us to know so we can get a little bit better at it. Recall that the maximum value when we talk about cos is actually 1. Now, I want to put in a little bit of a symbol on it. Those vertical lines should ring a bell back from Unit 1, us talking about an absolute value function. So the absolute value, if I don't care about sign at all, positive or negative, just the number for cos is 1. That is when my adjacent side is the same length as my hypotenuse. Also, the maximum value of my sine x, the same thing, absolute value of it, is also 1. The largest it can be is when my opposite side is the same as my hypotenuse. So we should be good then that there is no possible solution to the equation sine x equals 2. Because there is no possible way where my opposite side could be larger than my hypotenuse. So just to bring that idea back then, maybe we can see that right in the given equation, you know you have a special case. Your cos x equals 1, not a value less than 1. And so as we start to get more experience with this, we'll recognize that we're already dealing with an axis solution. Okay, as we take a look at E, I want to come back to that idea of cast rule again, because there would be a bunch of people that would really like cast rule, and I want to challenge you on E. That says when sine x equals 0. So if our instinct was to then go and put on our rotation angle, or our axes, and now try to figure out, well, what quadrant is sine 0? Well, 0 is neither positive nor negative. And so we would have to come up with a special case to be able to solve that. I think our reasoning using SOHCAHTOA and using coordinates is a better one. We can get there directly. So the first thing I'm thinking about is my sine. My sine is equal to 0. And I know that that means that my opposite side equals 0. Well, where does my terminal arm have to exist if there is no opposite side? Well, the only place where I can have no opposite side is if I'm directly across. So there could be the two positions that my terminal arm could lie in. So what angle measurements would get me there? Well, to lie on the positive x-axis, my x value could be 0. Or to lie on the negative x-axis, my angle measurement could be 180 degrees. I want you to watch out that we don't make a mistake here. Remember our restriction that x could be greater than or equal to 0 and less than or equal to 360. And so I could get onto that blue terminal arm on the positive x-axis if I did a full rotation, which means I actually have a third solution for this one, that I could get back to 0 or 360 degrees. Okay, I think we're at a point where we can start off some of these problems on our own. So I want you to take a look at question F. And what I want you to do is to go ahead and put on a quick set of axes. And now I'd like you to draw the terminal arm in the quadrants you think that it should lay. Go ahead and pause the video. Okay, we're back. And so, as we're back, we should be taking a look at our sine ratio. And so, our sine gives us a positive value, and therefore, I know my opposite side is positive, so I am going up. So, my terminal arm, and you drew your terminal arms in good spots if we have them in quadrant 1 and 2. Okay, now what I'd like you to do is I'd like you to drop in your heights, create your triangles, and label them. Go ahead. Pause the video. Okay, we're back. And so we dropped in a height and we dropped in a height. And since we're talking about sine, sine is opposite over hypotenuse. Or sine is opposite over hypotenuse. And we're good. Okay, this is where we're going to hit a bit of a snag. And where we hit the snag is we should recognize that an opposite side of 2 and a hypotenuse of 3 does not represent a special angle. And so we're going to need to use our calculator for this. And this is an instance where you would not be able to solve for an exact value of x. We're going to have to solve for an approximate value. So now that I've got that, what I need to calculate is this possible value for x. And so if I was to go through and calculate that value for x, I know that x is going to be the inverse sine of 2/3. And if we follow our general rounding rule, that'll come out to about 42 degrees. And so I know that this related acute angle then must be 42 degrees. Well, if that angle is 42 degrees, then this related acute angle must also be 42 degrees. And we can then solve for x by saying our terminal arm is in quadrant 1, or it's in quadrant 2, which would be 180 minus 42, or 138 degrees. So if we recognize that our ratio does not provide a special angle, then yes, you're going to have to use your calculator to be able to work back to an approximate. If an exact value is possible, then you are expected to state an exact value. Only when it's not a special triangle can we give approximates. Okay, and now you guys see the last problem for today, tan x equaling -2. So what I'd like you to do is pause the video and let's give this one a shot going start to finish. I would argue that if you're able to work your way through G, I don't think you're going to see anything in your practice that would cause you a problem. So pause the video now, give it a shot. Okay, we're back. So the biggest thing as we're working through this problem is you feel free to pause the video at any time once you've kind of found where we are along the way. So first thing we do, put on our axes. You saw that tan was negative. Tan is opposite and adjacent. Both of those can change signs. So the only way I can have a fraction that's negative is if I have different signs. And where is my opposite and my adjacent different signs? Well, maybe I'm to the left and up, or to the right and down. So hopefully we have our terminal arms in quadrant 2 and 4. Okay, as I said, feel free to pause it at any point to then find your mistake and progress through. Okay, we drop in our heights. And now we can go ahead and we can label those. Tan is opposite over adjacent. So maybe I have an opposite side of -2 and an adjacent side of 1. Or maybe I have an opposite side of positive 2 and an adjacent side of negative 1. There's my two triangles for me to now solve x. Okay, we recognize that that is not a special triangle, and therefore we're going to have to use our calculator. I'd just like you guys to notice that there is a really common mistake here. The common mistake is going to be to write that x is equal to the inverse tan of negative 2. And what you're going to notice if you push buttons on that is you're going to get something that looks a little different on your calculator. So let's make sure that we're good again on what we're actually solving for. We are solving for the related acute angle. And I'd like you to notice that your related acute angle is not x. So let's make sure that we don't label that as x. Now, a general form, maybe we go through and we call that related acute angle beta. And so if you wanted to go through and solve for beta, beta is the inverse tan of... Now, when you write down that negative 2, you're going to notice you get the same weird-looking answer as what we found before. Here's the issue. This negative on the 2, you already used up. You used that negative to determine where the terminal arm should lay. So we don't use it then to be able to go through and find the size of the angle. The negative refers to location. The number refers to size. And so now if we do the inverse tan of 2, we're going to come up with something that looks approximately like 63 degrees. And so my related acute angle in each triangle is 63 degrees. That would then give me a primary angle, or my solution for x, of being 60 degrees short in quadrant 2, which is 117 degrees, or 63 degrees short in quadrant 4, which would give me 297 degrees. And there we go. So there is our introduction into being able to solve pretty straightforward trig equations. Your job now, jump in and get as much practice as you can. You want to make this a pretty automatic process. Solving a trig equation, you're aiming for about 30 seconds to 45 seconds for each one. Good luck.